Hello. Today I'd like to talk a little bit about impedance admittance conversion, which is really just going from Z to Y given a particular value for one or the other. The reason that it's a little bit interesting to look at is we can look at the values directly on the Smith chart and see what that looks like as well. The fact that impedances and admittances are complex values makes the conversion slightly more complicated. So if we have an impedance, say, of R, a resistance, and a reactance, then based on the rules of algebra for complex numbers, y is going to be not equals to, you can't just simply take the parts individually and take their inverse. You have to take the inverse of the whole. And what that means is that you end up with an expression after doing the algebra that looks like something like where the resistance and reactance end up in the numerator. The sign of the reactance changes, and that's all over the magnitude of the complex quantity squared. And that's a result of having to, when you take the inverse, you don't, with complex numbers, you don't want the J operator in the denominator. So you do a process called rationalization, which is multiplying top and bottom by the complex conjugate. And so you end up with this expression. And that's how you convert to over to admittance if you're given an impedance. So y equals 1 over z, and that's what the 1 over z ends up looking like after all the complex manipulation. Now, what we can do is we can take a numerical example and look at that on the Smith chart. So, for example, let's take a normalized value of z equals 0.4 resistance plus J 0.2 for the reactance. And since it's a positive reactance, that basically means that it's an inductive reactance. And we can convert that to admittance simply by plugging the numbers into the formula and seeing what numbers come out. But what's a little bit interesting, as I said before, is to look at it on the Smith chart. And I just happen to have a Smith chart available. So, okay, and my Smith chart's kind of just bumping up against the left edge of the screen here. But let me take this value, see if I can move it over so we can sort of keep an eye on it. There's our impedance. And what we want to do is plot that on the Smith chart. And we'll be able to see then, right on the chart, the equivalent admittance. All right, so we need to find 0.4 plus 0.2. So I think what I'll do is I'll zoom in on the chart a bit. So we can read it better. And we're going to be looking at the red circles because we're talking about an admittance. Okay, so I can see here that, let me circle the values. We're looking for plus 0.4, so there's 0.4, and plus 0.2 on the reactive circles. So our impedance is going to be at the intersection of those two curves. So let me just go ahead and draw that. Sort of changing the pens around a little bit. Let me get a fat pen going. Okay, so if I follow this curve, the 0.4 curve up, I won't draw the whole thing, and I'll draw this 0.2 curve out. Here's the intersection of the two of them, and that's our impedance. And so now on the chart, we can simply read off the equivalent admittance. And if I just follow the blue curves, we're sort of running on this blue curve here. Don't want to cover up the number. And then that's the conductance curve, and we see that it intersects with the 2.0 conductance. And then I'm going to have to move a little bit to read off the admittance, the susceptance curve. Let me zoom out just a bit to get things back on the screen. Hopefully we can still read the numbers. But if I follow the blue susceptance curve out, I can read that the value is 1.0. So from the chart, we can graphically get the equivalent admittance. So let's go back over to our calculations here. And let me just go back to 100% and bring our equations back over here. If we do the math, what we would get, go back to the same color, we'll get 0.4 minus j 0.2 over 0.16 plus 0.04. And that gives us, so these end up being 0.2. So we get 2 minus J1. And looking back over at the Smith chart, that is indeed what we got. Here's our 2 for the conductance, and in the admittance chart, the upper half of the chart is negative values, and so there's our -1. Okay, and so another thing we can do graphically is we can look at what does happen if we take the reciprocals individually and where that puts us on the chart. So if we take our impedance and take the parts reciprocals individually, we get 1 over 0.4 gives us 2.5, and 1 over j 0.2, again it flips the sign because of the j when you take the inverse of that, j 5. So minus 2.5 minus J5 is what we end up with doing it the wrong way. But we can see those values on the chart. Let's zoom back in here. And here's our point again in the middle of all these crosses. But if we take the inverses, the reciprocals of the parts individually, we end up with following these circles. So instead of finding the intersection and of the corresponding admittance circles, we just take if we take the parts individually, what we're essentially doing is finding the intersection of the individual circles that match up with the individual circles from the impedance. So here's 0.4 where the 0.4 impedance intersects with a conductance. That's the resistance, and the corresponding conductance. That's going to be our 2.5 value. You can see it's between 3 and 2. And then for the reactance, if we convert that independently to a susceptance, we're just going to follow this curve. The inverse of 0.2 is 5.0, and again the top half of the chart is negative. So let me continue this circle around. And so the point that we get is a totally different point than where we started. And it doesn't give us the correct answer at all. But you can see that graphically on the chart. So it doesn't work algebraically, and it also doesn't work graphically. So we'll just come back over here. That is not the way to do it. You have to follow the algebra correctly. Okay, and so one last look here, one last concept or way of saying the same thing over again. We can look at this in terms of what kind of equivalent circuits we're describing. So if we're given an impedance, its simplest circuit description will be a resistance. Actually, let me switch back here. A resistance in series, since we have a positive reactance, it's going to be an inductor. And in the normalized terms, the resistance is 0.4 ohms, and the reactance, as we said, is 0.2, J 0.2. And this is we can calculate what the inductor value is if we know the frequency, because that is a frequency-dependent component. And what we have learned, or what we have determined, is that the equivalent admittance, or parallel circuit, is 2 minus J 2 minus J1. So what that implies is the simplest parallel circuit is going to be a parallel conductance with a value of 2 ohms, mhos, and a parallel inductor with a susceptance of minus J1 mhos. And again, we can calculate what the actual inductor value is if we are given the frequency. So these two circuits are equivalent. We'll give the equivalent input impedance or admittance at one frequency. The frequency dependency comes from the fact that the reactance or susceptance varies with frequency. So these will be equivalent only at one frequency. But they give the same performance. So that implies if you are developing a circuit and your calculations achieve some component values that are unrealistic, for example, you could see whether the equivalent, if you had a series circuit, you could see whether the equivalent parallel circuit gave you some more realistic component values and substitute that in, as long as you only needed the performance to work around one particular frequency. The circuits will have the similar performance over a range of frequencies. That depends on what the Q of the combined circuit is. A high Q circuit will have a narrow range of frequencies over which the equivalency holds. All right, so that's kind of a long look at impedance and admittance conversion, but the nice thing is that it shows up graphically on the Smith chart. Bottom line is you need to follow the rules of algebra, but you can actually see the way that those values play out once you know how the Smith chart works. So that can be also of interest. All right, hope you enjoyed the video, and we'll see you next time.